Unsteady Compressible Flows. La thèse a été co-dirigée par la professeure Paola Cinella de Sorbonne Université et Anka Belmé, ici présente. Donc vous avez habituellement 3 quarts d'heure et ensuite le jury posera des questions et ensuite il y aura la délibération.
Okay, so thank you, Madam President. So thank you all for being here. Today I'll present you the work I did during my 3 years of PhD. So I worked on adaptive grid refinement for unsteady and compressible flows under the direction of Paola Cinella and Anka Claudia Belmé. So I did my PhD here at Institut Jean Léron d'Alembert at Sorbonne Université. So for the context and the motivations of this PhD, so this PhD is part of the MAMBO project. So MAMBO for méthode avancée pour la modélisation du bruit moteur et avion. It's funded by the General Direction of Civil Aviation. So we have a close collaboration with the industry, especially ArianeGroup and Airbus. And the general goal of this project is to improve the representation of aerodynamic noise sources in turbulent flows. Here I have some examples of noise. Here in the figure A, we see noise that is induced from a binding area on an Ariane 5 space launcher. On the image B on the right, we have noise that is induced from a turbulent jet. And on the image C, on the down part, we have the noise footprint of a 747 aircraft in blue and the noise that is induced from an A350 aircraft in red during takeoff. So the motivation of this project is to understand and predict the behavior of these noise sources, which itself is a very complex phenomenon. So how can we understand and predict these noise sources? So there are several approaches in the literature. One of the approaches is to fully numerically resolve the Navier Stokes equations. So we do this using CAA methods, so computational aeroacoustics, where we simulate both the fluid dynamics and the resulting acoustic fields. So here we have an example of CAA of a fan noise that is induced by a realistic coaxial engine. So the advantage of these methods is that we are able to capture all the relevant flow structures and acoustic phenomena within a single computation. However, we need very fine meshes for these types of methods. So the CPU cost becomes very quickly too high and thus prohibitive. So for that, we adopt hybrid approaches. So in the hybrid approaches, we separate the aerodynamic acoustic sources and the propagation. So in these approaches, they offer greater accuracy and they're more computationally feasible. However, there are aerodynamic acoustic sources that are generated by these turbulent flows, so we have the need for accurate flow computation. So until now, the industry used widely runs, so runs for Reynolds-Averaged Navier Stokes. So these methods were cheap, however, there was a lack of accuracy. So for that, today and in general, now hybrid Runs-LES models, they have become more of an attractive solution for industrial applications. So here we have the hybrid Runs-LES. So we combine runs and LES. So runs for the mean flow, LES for the larger turbulent structures. So here, these hybrid Runs-LES, they are between, as we see, the LES and the DNS and the runs. So they are a compromise between these kinds of methods. However, these models, they are very sensitive to the computational mesh. And this is because of the filtering operator in LES that is directly proportional to the mesh size. So our way to deal with these issues is to use dynamic mesh adaptation for unsteady turbulent flows that we call DMA. So what is dynamic mesh adaptation? Is the automatic optimization of the computational mesh. So DMA offers many advantages. However, there are also several challenges. So for the advantages, we have an efficient use of the computational resources. We are able to focus refinement only on critical regions of interest and not in the whole computational domain. And we have a reduction of the computational cost compared to uniform refinement. However, as I said, there are several challenges. So first of all, DMA methods are pretty complex to implement, especially in industrial codes. There are also error estimates that are problem dependent, which means that an error estimator that is good for one problem might not be good for another problem. We also have problems coming from the fact that we couple with mesh-sensitive turbulent problems, which means that we introduce supplementary modelization errors. And we also have problems coming from the fact that we deal with unsteady flows. So, because industrially wise, it's very computationally expensive to adapt in every time step the mesh, we need to define this period of adaptation. So, because we do not adapt in every time step, we introduce the problem of the solution mesh delay, which means that our mesh has a delay with respect to the solution. So that means loss of important information. So now that we saw the context and the motivations, we are going to see the outline. So first of all, we're going to show some adaptive techniques that exist in the literature. We're going to see the governing equations and the numerical methods that we use. We're going to see the adaptation strategy that we use, some numerical results that we obtained during this PhD, and finally, we're going to draw some conclusions and perspectives. So first of all, we're going to show some adaptive techniques that exist in the literature. So here I have 3 examples of adaptive strategies that exist in the literature. The first one is H adaptation. So in H adaptation, we have a subdivision of the cell. So here is an example of H adaptation for a lifting hydrofoil geometry colored with the water volume fraction. Then we have the example of P adaptation. So in P adaptation, we have an increase of the order of the polynomial approximation, and here we have an example for a circular cylinder at Reynolds 40. And finally, we have HP adaptation. So in HP adaptation, we have both H and P. So H for the subdivision of the cell and P for the change of the order of the polynomial approximation. So here we have an example of an HP adapted mesh for a P prime nozzle configuration. So here in this PhD, we will focus on H adaptation. So how do we perform H adaptation? We perform it using error estimators. So there are several error estimators in the literature, especially when we deal with turbulent flows. So for example, we have the case of Bernard and co-authors in 2016 that they proposed a combination of mesh refinement criteria. So the first one to account for the interpolation error, and the second to make sure that enough kinetic energy was resolved. So this second criterion is very similar to the Poe criterion, where we have the sum of the subgrid and the resolved energy that says that if this ratio is approximately close to 80%, we have enough turbulence resolved. So after that, we also have the case of Antepara and co-authors in 2015, that he proposed an error estimator that is based on the velocity residual, so a mostly heuristic error estimator. Then we have the case of Tusi and co-authors in 2017. So these researchers, they base themselves on the fact that the filter width scales with the grid width. So they proposed a directional anisotropic error estimator that is based on the small-scale energy coupled with a modified filter. Also, they proposed another error estimator that is the structure function. So the structure function is a function that has been widely used in the literature, and it's related. It has been proven to be related with subgrid stresses. So normally, larger values of the structure function, they denote the need for more refinement, and lower values of this function, they denote mostly laminar conditions. Then we also have the error estimator proposed by Bastien Sauvage in 2024, in his PhD. So Bastien, he proposed a Riemannian metric, and he enriched it by the Tusi and Larson error estimator. So he calculated optimal cell size, and he enriched it by the error estimator, the first error estimator that was proposed by Tusi and Larson in 2017. So as we see here, there is not a universal error estimator for turbulence. So until now, there are some open questions that we are going to try to answer during this PhD. So first of all, we saw that there is not a universal error estimator in the literature, especially for turbulent flows. So which adaptation criterion should we use when we deal with these kind of flows? Second of all, how often should we adapt the mesh? If we adapt very often, then the CPU cost becomes very high. However, if we do not adapt so often, we have the problem of the solution mesh delay, which means that our mesh has a delay with respect to the solution, so loss of important information. And third, in the context of our acoustic cases, does DMA cause any parasitic noise? So we are going to try to answer these questions during this PhD. So now I'm going to explain the governing equations and the numerical methods that we use. So first of all, we look for numerical solutions of the compressible Navier Stokes equations. So here we have omega CV, the fixed control volume with a boundary ACV, and the outer normal vector, W, the conservative variable vector, and F, the flux density. So F is the sum of the Euler and the viscous fluxes, with ρ, the density, U, the velocity vector, P, the pressure, taf, the viscous stress tensor, QH, the heat flux vector. So to modelize the turbulent heat flux, we use a turbulent Fourier law with a constant turbulent Prandtl number. We use the Boussinesq hypothesis, and finally we determine the eddy viscosity by means of a hybrid Reynolds-Averaged model. So which turbulent model we use? So we use the delay detached eddy simulation model, which allows for an optimal blending of Reynolds and HRLES. So this is a model that has been widely used, especially in the literature. It's based on the compressible K omega SST model. Here, the transition from Reynolds to HRLES is controlled via a shielding function FD and the modified distance DDOS. So here, the role of the shielding function is to protect the attached boundary layers. And finally, the eddy viscosity is dynamically adjusted based on the grid spacing delta and local flow structures. So for the numerical discretization, we discretize by means of a finite volume on unstructured grids. So here we have a sketch of a 2D mesh on the left. So here we have omega j, our cell, xj, the center of our cell, omega k, our neighboring cell, and xk, the center of our neighboring cell, with agk, the boundary. So here we define a spatial average, a psi j bar, and its pointwise value. here are our unknowns are the volume averaged values, and finally our system takes this form with the fluxes that are approximated using a k-exact finite volume scheme, and we use here high order accuracy is achieved by reconstructing the solution locally in each mesh cells using polynomials. So here we use a numerical scheme of third order. So here this third order accurate scheme is constructed by using a high accurate approximation formula for these flux terms. So here the flux function is f is expanded using a Taylor series around an integration point gamma of AGK. So here, in order to calculate this term, we need to know the flux gradient at point gamma, the flux Hessian, and the surface moments. So in order to achieve, to have third order, we need to reconstruct F gamma at order 3. We need to reconstruct the flux gradient at order 2 and the flux Hessian at order 1. So we said that to achieve a third order approximation, the flux and its derivatives must be reconstructed from the volume averaged values. So here we apply the reconstruction to the primitive variables Q. So these are the relations that link the conservative to the primitive variables. So for each cell omega j, we introduce the tilde vector qj tilde that is obtained by using the previous relations to the volume averaged conservative variables. So here qj tilde, there are only second order approximations of the pointwise values of the primitive variables at the cell center xj, which means that by doing that we introduce an error term of order 2 that we need to correct. So how do we achieve to increase the order? We pass through a method of successive corrections to correct the errors that have been introduced during this procedure. So here I'm going to we're going to see the steps that we follow to calculate finally the fluxes. So as we said, the first step is to go from the conservative variables W to the primitive variables Q, which introduces this error of order 2. Then we follow the flash from 1 to 2, so the tilde values to the volume average values. So this step is important because we introduce this delta Q term, that is a correction term that we are later going to use for mesh refinement. Then we follow the arrow from 2 to 3, so we go from the volume averaged to the cell-centered pointwise values, so in the center of the cell. Then we pass from the cell-centered pointwise values to the cell face. We apply a Riemann solver and a recentering strategy that was done in the PhD of Pont in 2015. And finally, we calculate the fluxes. So now that we saw the governing equations and the numerical scheme that we use, we're going to show the adaptation strategy that we use. So we apply our developments on the Flussepa solver. So the Flussepa solver is the flow solver of ion group. So Flussepa is an unstructured finite volume 3D unsteady viscous solver. It has a conservative grid technique with intersections. A hierarchy of grid patches with priority levels is used, and the numerical discretization is conservative. So what about mesh refinement in Flussepa? So in 2017, Limar introduced this cell-based octree for Hexhydra. So how do we perform mesh refinement in this code? By using error estimators. So until now, we used heuristic criteria to perform mesh refinement that were mostly based on a pressure Hessian or a velocity Hessian, for example. So for the general methodology. So until now, we use the instantaneous fields to compute the adaptation criteria at a fixed adaptation period. So this introduced several problems. So the first problem was that we saw that the error estimators that we used were not adequate for scale resolving simulations. The second problem that we had was the solution mesh delay problem, which meant that because we did not adapt at every time step, then our mesh had a delay with respect to the solution. Then we also had another problem, which we call over-refinement, which means that we didn't have a way to stop refinement after our calculation had statistically converged. So we adopted a new adaptation strategy. So first of all, we found a new error estimator. Second of all, to deal with the solution mesh delay problem, we used the time average of the instantaneous criteria. And third, we coupled it with an automatic period control technique. So first of all, we found a new adaptation criterion, which we call truncation error criterion, so take Q. So here we wanted to create an error estimator that was purely based on the numerical scheme that we use. So here our goal is to propose to use the approximation errors estimated during the correction procedure to control mesh refinement. So we developed this error estimator epsilon j, that is the difference of the pointwise value at order 3 minus the pointwise value at order 2. So this error estimator, it has these two terms. So we have the delta q1 term and the delta q2 term. So this correction term, delta q, it depends on the primitive variable that we use. So if this it can be based, for example, on the velocity, on the pressure, on the temperature. Here we have an example for the velocity for this delta q term. So here we have the average velocity minus the numerical velocity. We also need the volume moments at order 2 and the gradient. So after that, we apply the Cauchy-Schwarz inequality to obtain an upper bound on the error, which gives us finally this error estimator that we call truncation error criterion. That is the sum of the absolute values of the delta q1 correction term and the delta q2 correction term. So now that we defined this new error estimator, we want to couple this error estimator with a strategy for unsteady flows to deal with the solution mesh delay problem. So for that, we use time average criteria from the instantaneous criterion. So as we said before, because it's very costly to adapt in every time step, we need to define this adaptation period. So if this period is not set properly, then we lose important information. So we calculate the mean criterion at adaptation n. We also, similarly, we also compute the mean criterion at adaptation n plus 1 with delta t equal to the difference of tn plus 1 minus tn. So we finally calculate the mean criterion at adaptation n plus 1 using this spatiotemporal formula. Here we need to say that we use the mean of the instantaneous criterion and not the criterion of the mean flow. And this is because the effectiveness of the first method was already proved in the literature. So after that, we want to deal with the problem of the over-refinement. So what happens when our calculation has statistically converged? How do we stop mesh refinement? So we need to find a way to automatically control the period of adaptation. So for that, we calculate this simple ratio epsilon. So this simple ratio epsilon, on the numerator, we calculate the L2 norm over the whole computational domain of the mean criterion at adaptation n plus 1 minus the L2 norm of the mean criterion at the previous adaptation over their sum. So why do we calculate the L2 norm on the whole computational domain? This is because our mesh changes between adaptations. So this gives a number between -1 and 1. So if epsilon is positive, then it means that our current error is way bigger than the previous error, which means that we need to refine more, hence the adaptation interval needs to decrease. However, if this epsilon is negative, it means that our current error is smaller than the one before, so we need to adapt less, hence the adaptation interval needs to increase. So now that we explained the strategies that we use, I'm going to show you some results that we obtained during this PhD. So the first case that we use is the evolving mixing layer. So here we are at a convective Mach number of 0.6 and at a Reynolds number of 500. So here we have a fluid with two different velocities that creates an evolving mixing layer. So after that, we conduct some calculations using the instantaneous take Q, the mean take Q, the mean plus the APC technique take Q. We apply one level of refinement, and we start from a very coarse mesh of 240 times 60 elements with no refinement. And we compare ourselves with a reference solution obtained on a uniformly refined mesh of 480 times 120 elements. So here you see the instantaneous. We plotted it using green, the mean with blue, the mean with the APC with red. Here we have the dotted blue for the coarse mesh with no refinement and the dotted black for the reference mesh. We see that in this case, the mean criterion with the APC technique seems to capture better the reference solution in terms of velocity and pressure profiles. So after that, we also calculate the relative CPU number and the relative cell number. So we calculate these results with respect to the uniformly refined mesh of 480 times 120 elements. And we see that in the three cases, we take almost 1/3 of the time, and we obtain almost 1/3 of the cells. We also see that when we use the take Q with the time averaged and the APC technique, we have a CPU time that is lower because of this variation of the adaptation interval. So after that, we compare our take Q error estimator with the pressure Hessian error estimator. So here I plot the velocity and the pressure profiles obtained using the time averaged and the APC take Q in red. And I also compared with another error estimator that is heuristic, which is the pressure Hessian. So I plot this with blue-green, and I compare it with a reference solution of 480 times 120. We see that our error estimator in terms of velocity and pressure profiles seems to better capture the reference solution. So this is almost also due to the fact that the pressure Hessian we calculated using the Frobenius norm, and the take Q criterion here is based on the pressure, and it contains many terms. So after that, I compare our results in terms of relative CPU time and relative cell number, and we see that with both criteria, our DMA technique arrives to almost 1/3 of the CPU time and 1/3 of the cell number. Here I show a little bit better the peaks. So after that, we want to complexify our test case and see if our error estimator is also able to capture shocks. So again, we have a fluid with two different velocities that creates an evolving mixing layer. This time we also have a shock, an oblique shock that originates from the top left of the domain. It impacts on the evolving mixing layer, then it impacts the lower boundary and again reflects and impacts on the evolving mixing layer. So here we also conduct some calculations. So first of all, we have a reference solution that we found in the literature obtained by Yi and co-authors. So we have the pressure contours that were obtained by Yi and co-authors in the image A. In the image B, we have a reference solution that we obtained on a uniformly refined mesh of 960 times 240 elements. Then the image C is the pressure contours that were obtained starting from a very coarse mesh of 240 times 60 elements with 2 levels of refinement. And here I show a zoom of the mesh. So we see that we are able to capture the oblique shock, and the reflected shock, as well as the vortical structures by using this error estimator. So after that, I also compare the error estimator using the time average criteria and the APC technique with a pressure Hessian criterion, as I did before. And I compared with the reference solution of 960 times 240 elements, and we see that in terms of pressure profiles, with this error estimator, we are able to better capture the reference solution than by using another heuristic-based error estimator. So after that, we want to test our strategies for a turbulent case. So we take the axisymmetric backward-facing step. So here we are at a Mach number of 0.7 and at a Reynolds of 1.2 million that is based on the diameter. So here on the image on the left, we have our initial mesh that is composed of intersected meshes with 6 levels of priority. So after that, we conduct 3 calculations using our TQ error estimator. So here we have our initial mesh, so with no refinement. Here we have a snapshot of the mesh that was obtained using the instantaneous TQ criteria. Then the image B, it represents the mesh obtained by using the time averaged TQ, and the image C, it represents the mesh obtained using the time averaged TQ with the automatic period control technique. So we see that in the 3 cases, we are well able to adapt in the shear layer and in the recirculation bubble, while no mesh refinement occurs in the attached boundary layers. We see that when we use an instantaneous criterion, we obtain a mesh that is more scattered, which is logical because we use instantaneous fields. And when we use the time averaged and the time averaged with APC, we obtain a mesh that is more uniformly refined. We also can say that with the instantaneous criterion, we arrive to approximately 11 million elements. With the mean criterion, we arrive to 10 million elements, and the same with the APC technique. However, this technique, it takes less time because of this variation of the adaptation interval. So here, this figure, it shows a snapshot of the Q criterion, so colored by the velocity magnitude. So in this figure, we see the shear layer instabilities, the development of the hairpin vortices, the three-dimensionalization of the flow, and the breakdown to turbulence. Interestingly enough, we see that when we use instantaneous criteria, we see here the solution mesh delay problem, which we do not see when we use time averaged and time average criteria with APC, and this is because we have a more uniformly refined mesh in the shear layer, which favors the development of instabilities. So for a more quantitative assessment, we also calculate the wall distributions of the time average pressure coefficients and pressure coefficient fluctuations of the several meshes with experimental data and a reference solution of Pierre-Lévy. So we take this reference solution because Pierre-Lévy obtained his results using a mesh of approximately 12 million elements that is very close to the ones that we obtained with our adapted meshes. So here I plot the instantaneous criteria with yellow, the mean criteria with blue, the mean with APC with green. I plot the reference solution with red and two experimental data. So the first is with black, and it's from Meliga, and it was obtained using the steady taps method. And the second is obtained by Meliga using the Coolite method. We see that in terms of CP, we have satisfactory results in terms of CP. So our three results using the three adapted meshes give us satisfactory results in agreement with the experimental data. However, in the terms of CP-RMS, we see that the time average criteria give more satisfactory results than the instantaneous criteria. So after that, we also want to have also calculate the turbulent scales. So here on the left, I show the mean flow of the calculation used using the mean criterion and the APC technique. What we do here is that we calculate our turbulent scales on two different positions. So here on the shear layer and in the recirculation bubble. So we make the assumption that we are locally homogeneous and isotropic, and we calculate the integral scale. So the integral scale is equal to the modeled and the resolved over the dissipation rate. We calculate the beginning of our inertial scale, the beginning of our dissipative scale, the Taylor microscale, and the Kolmogorov scale. We see that in the three cases, our minimum cell size is way below the integral scale and way above the Kolmogorov and the Taylor microscale, which is satisfactory for us because we only want to capture very, very large structures of turbulence, and we do not want to go towards LES or DNS. So after that, we also plot the ratio of the grid size over the integral scale for the three computations. So this ratio, it's important because it measures how fine the grid is relative to local characteristic size of the larger turbulent structures in the flow. So we see that in downstream of the step, we have a ratio that has values between 0.01 and 0.005, which means that the local grid sizes are about 2 orders of magnitude less than the integral scale. So after that, we also conduct a spectral analysis. So we have some experimental data that denote that in different locations in the recirculation bubble, we should obtain different Strual numbers. So for that, we calculate the normalized power spectral density of the pressure in function of the Strual number. So here what we do is that we calculate the power spectral density from 4 equally distributed captors around the backward facing step. So here I plot the results that were obtained using the time average criteria and the APC technique. So we see that we are well able to capture the dominant frequencies around Strual number 0.1 and 0.2 at the streamwise location x over d equal to 0.6, as well as the dominant frequencies around Strual 0.2 and 0.6 for the location x over d equal to 1.2. So after that, we also have, for a different location, in the backward-facing step, we have some experimental data that are available in the literature. So the Depré is depicted here with the blue dots, Meliga with black, the reference solution of Pierre-Lévy with red, and our DMA calculation with the APC technique in green. So we see that we are again well able to capture the dominant frequencies around Struble number 01, 02, and 06. So for the conclusions, we developed a novel error-based refinement criterion that is based on the K-exact finite volume scheme. We were able to successfully apply these strategies using the TEC criterion in cases of increasing difficulty. We implemented the time averaging for refinement criteria. That is something that is pretty easily generalizable for any DMA framework. And we also dynamically adjusted the mesh adaptation period, which is also something that is generalizable for any DMA framework that deals with unsteady applications. For the perspectives, we would like to combine this TEQ criterion with a more physics-based criterion, for example, the Pope criterion. We would also like to explore anisotropy with a software that's called Tucanos. That is a software that is already coupled with Frusepa. And we would also like to apply the methodology to our acoustic cases. Here I just demonstrated some preliminary results. On the left, we have an acoustic pulse that we conduct mesh refinement using the TEQ criterion. Here on the second case, I have an example of a flow around a cylinder at Reynolds-150. Here our goal is to be able to capture both the sources and the propagation using only one criterion. And here I have a preliminary result of the DMA application using heuristic criteria on a P prime jet. Thank you for your attention.